Hello, everyone. Thank you for being here on the last day of the conference. I'm Hsueh-Tsung from University of Michigan. The other two authors are Dr. Yutao and Dr. Yogesh Gianchandani. So the title of this work is a hybrid evolved for gas chromatography systems. And to begin with, I would like to talk about So to begin with, I would like to talk about the motivation behind this work. Microvalves have received substantial attention from both industry and academia for various applications such as microgas chromatography, drug delivery, and space cooling. And microscale gas chromatography is the intended application of this work. So why do we focus on gas chromatography and why is it important? So GC has been adopted by petroleum industry in 1950s, and since then, its use has been extended to several different fields such as food analysis, drug analysis, and especially air pollutant sensing. Indoor air pollution, which is mainly caused by volatile organic compounds, is one challenge GC is aiming for. And this is a serious issue since VOCs can cause severe health hazards, and some of them are even carcinogens. And this is why environment sensing technology and GC are important. This photo shows a benchtop GC. It is bulky, and its sample collection and injection requires manual labor. Hence, micro GC has been developed for over decades. So since the application is micro GC, the required features of microvalve is defined by its operation. General micro GC usually includes a bidirectional pump module, pre-concentrator, microvalve, microcolumn, and microdetector. The microvalve is used to control the direction and timing of flow, which requires the feature of three-way control with low depth volume, chemically resistant to volatile organic compounds, large open-close ratio, low power consumption, and robust and simple. So the goal of this work is to develop a microvalve with all these features. Here are some photos of commercially available microvalves, and most of them utilize solenoid actuation, which consumes more power than piezoelectric actuation, and none of them meet all the above-mentioned requirements. So this is the reason why we're developing our piezoelectric valve. One thing I do want to mention is that conventional piezoelectric microvalve usually have a thin membrane fabricated on silicon wafer with some specific features. Such fabrication of such structure could require several lithographic masks, precise time control for wet etching, or anodic bonding. So it can be seen that the fabrication is pretty time consuming, hence simplifying fabrication is one of our goals. So with this goal in mind, we have several challenges. And the first challenge is the design of architecture itself. The valve requires three-way control with low depth volume and energy consumption smaller than 1 millijoule per switch. The second challenge is the assembly process. So since the displacement generated by this piezoelectric actuator is usually around tens of micron range, which could easily be sacrificed during the assembly process. Hence, assembly is always a challenge for this piezoelectric microvalves. The third challenge is the prefabricated valve membrane. So as I mentioned, to get rid of the thin membrane fabrication, we propose to use a prefabricated membrane. Hence, the selection of the prefabricated membrane is a challenge. And the fourth challenge is the fabrication process. So I'm going to show you how we address these issues one by one, and this is the first one. So this is the new architecture we propose, and the reason we call it a hybrid valve is because it combines prefabricated components and microfabricated components. Besides prefabricated piezoelectric actuator, we also utilize prefabricated valve membrane, which allows a simple and robust implementation. So the microvalve has microfluidic channels in the center, which is called fluidic die stack because it's formed by 3 silicon dies. To illustrate how the flow is routed, let's imagine when the gas comes in from the inlet, it will go all the way to the center. And if the actuator is opened just like top side, the gas is allowed to travel through the membrane area and leave the valve at port 2. If the actuator is closed like bottom side, the gas will then be stopped. So each side of the fluidic die stack has a 2-layer polyimide membrane that serves as valve membrane. The inner membrane has polyimide side, non-adhesive polyimide side facing toward the substrate to provide chemical resistance, and the outer membrane has adhesive side facing toward the substrate, serving as an anchor and sealing the parameter. The estimated volume is around 0.96 microliter. Above the valve membrane is the piezoelectric actuator that is clamped by two O-rings near the parameter. The major purpose of these O-rings are to provide simply supportive boundary condition for the actuator to maintain its displacement, and I will have a slide discuss on this soon. So the energy consumption of this actuator is around 0.78 millijoule per switch. It can be seen there is a silicon pulse between these two components, which is used to mechanically couple the actuator and the membrane to transfer actuation. The softness from silicon also ensure minimum leakage at a closed state. So every component will then be accommodated by a customized two-part 3D printing housing with precise alignment, and the whole structure will be clamped by two disc magnets from both sides. So with such architecture, we're able to open and close the valve successfully without having any leakage to ambient. And this is how we address the first challenge. The valve does have three-way control with low energy consumption and low depth volume. So here we go, the second challenge. So to ensure the assembly process is phased out and straightforward, maintaining all the displacement from piezoelectric actuator is important. So this slide shows the estimate of displacement from piezoelectric actuator. So the actuator is able to generate around 100 micron displacement without any clamping. So it is expected the displacement should reduce after assembly just purely because of the clamping effect. And this is experimentally proved by us that if the actuator is not assembled into the valve properly, the valve is not able to function. So at the beginning, we have tried directly clamp the actuator onto substrate without any O-ring, and apparently this approach did not work because of a couple reasons. And one of the major reasons is that such assembly tends to provide fixed boundary condition, which could limit the displacement by a lot. So the top figure here shows the fixed boundary condition, and this is similar to the situation when we directly put the actuator onto substrate, since the substrate has a flat surface as well. So in order to address this issue, we introduce O-rings to our structure to provide simply supportive boundary condition to eliminate the clamping effect. And in a 2D analogy, the displacement could have a 5 times difference, which is significant. And this is the reason why we have to introduce O-rings to provide simply supportive boundary condition. So the takeaway message here is we have this O-ring clamping method to maintain a displacement, which is successful, and this makes our device work. So the third challenge is the selection of the prefabricated membrane. So this prefabricated membrane not only has to be chemically resistant to volatile organic compounds, but also have to have low surface roughness to eliminate leakage. So we have measured the surface roughness of several prefabricated membrane, and the first one is the piezoelectric actuator itself. So the surface roughness, again, says it's not a good idea to directly clamp the actuator onto the substrate. The second membrane we have measured is a Teflon FEP thin film. In the 2D image taken from the microscope, it can be seen there are a lot of scratches, spikes, which can lead to a significant amount of leakage. And this is not an appropriate candidate for our application. So eventually, we found this polyimide capstone membrane. So polyimide itself is chemically resistant to many volatile organic compounds, and the membrane itself has an excellent surface roughness, which is around 17 nanometer. So the message here is the prefabricated polyimide capstone membrane is an excellent candidate to replace traditionally microfabricated valve membrane. So with this prefabricated membrane approach, we're able to simplify the fabrication process. And here are the results in some photos. So the silicon die is microfabricated by two-side DRI, which only require 2 lithographic masks. The front side DRI, the first side DRI is used to create fluted channel, and the second step DRI is used to create through hole. So this fluted die stack is formed by bonding 3 silicon dies using a low viscosity epoxy, and the attachment of this capillary tubing is done by a high viscosity epoxy. So the fabrication is simple and straightforward, which only require 2 masks. But furthermore, we do not need any wet etching or any micromachining bonding process. So finally, here are the results we have. So the left figure shows the flow rate versus pressure head when the valve is open, and the right figure is the leakage rate versus pressure head when the valve is closed. So again, x-axis is pressure head in the unit of kilopascal, and y-axis is flow rate in SCCM. And The blue dot, since this is a three-way valve, so the blue dot shows the flow rate through outlet 1 when outlet 2 is closed, and the orange dot shows flow rate through outlet 2 when outlet 1 is closed. So the slope of this plot basically indicates the flow conductance, which is around 4.42 SCCM per kilopascal. And it can be observed that we have identical performance from both outlets, which means and proves that our assembly process is straightforward, that we are able to get repeatable results. So the right figure is then the leakage rate. This the y-axis is flow rate in a unit of microliter per minute, and basically this is 1,000 times smaller than SCCM. So the valve does have a tiny amount of leakage, but it demonstrates a high open-close ratio, which is around 3,618, and the valve is capable of bidirectional control. We have also tested the valve first as different voltage, actuated voltage, and it's shown in the lab. So the valve requires around 60 to 70 volt to be fully open, and it has same performance under different blocking pressure. Some hysteresis phenomenon from piezoelectric actuator was found by cycling the voltage from negative 80 volt to positive 80 volt. So although we do have some hysteresis phenomenon, this does not affect our operation since our application only requires fully open or fully closed. And this can be done either by driving the actuator either a positive 80 volt or negative 80 volt. We have also performed a preliminary lifetime test to prove the valve's reliability. The valve shows stable performance over 1,900 switches after 24 hours test. So here is the conclusion. So the hybrid three-way valve is designed and successfully fabricated and assembled using a phase-out process. The valve is chemically resistant to volatile organic compounds, which is an important feature. And the valve also has low power consumption. The valve also demonstrates a high flow open-close ratio, and a preliminary lifetime test was done to prove its reliability. So I would say the major contribution of this work is that we develop a new approach to construct a valve, which simplifies the fabrication process and improves the structural robustness. It further enables the operation of micro GC, which improves the environment sensing technology. Acknowledgement, we do appreciate all our colleagues for the assistance of fabrication and test setup. And thank you. This is all my presentation. I'll take any question.